In the last video, we started with a square path that we wanted a point to travel along. And we used arrows to indicate the direction of travel. And I also wanted to point out that it's pretty normal when you graph paths to actually include the timing information on the graph like this. That way somebody can see where you start and where you end. So our solution strategy to find equations for this was to start by graphing the x position and the y position separately as functions of time. And that let us use a tool that we already knew, parametric equations, piecewise defined functions, to write the equations. In this video, we're going to go the other direction. So I'm going to start by giving you some parametrically defined equations, not piecewise defined, just kind of some normal functions. And then we're going to go backwards. We're going to figure out what path they actually represent. So let's say that the x position as a function of time is given by t minus 2 squared over 10, and the y position is given by 10 minus t. But we're only interested in starting at time 0 and going to time 10. So you can graph this the way that you would ordinarily graph any function. You can make a table and plot points. So here we go. Notice the difference is because the independent variable is time, I'm going to list times in my left-hand column, and then I'm going to, rather than having two separate tables, I'm going to combine the tables for these two equations in one, so that I'll have the x, y separately, and it'll make a bunch of nice points for me to plot. All right, so here we go. Okay, so that was a lot of plugging and chugging. Now, let's do a lot more plugging and chugging by plotting the points. It looks like my smallest x coordinate is 0, which is the 0 divided by 10. And it looks like the largest one is down here, 64 tenths, which is the same as 6.4. So let's make 7 be the largest x coordinate. And y coordinates go from 0 to 10. So you'll notice that the point when time is 0 is the point at 0.410. So 0.4 is about there, and 10 is way up here. So that's our time 0. That's our starting place for the path. Next, when time equals 1, the y-coordinate is 9, so I've gone down. And the x-coordinate is 1/10, so it's closer to the x-axis, the y-axis, excuse me. And then when time is 2, we've got the y-coordinate is 8, but the x-coordinate is 0, which is here. And then it seems like the x-coordinates are symmetrically going to go back up again. So we had 4 tenths, 1/10, 0 tenths, and then back up 1/10, 4 tenths. Meanwhile, the y-coordinates continue to decrease by 1. So I should have a point here, and I should have a point there. So this has made a nice little, whoop. And then this one down here is when the time is 10. So if we're going to add arrows now, the path is starting here, going that way. So this obviously is a fairly imprecise sketch. Let's look at it on Desmos. And we didn't do too badly. We can now watch the point actually travel, and that's sort of what we expected to happen. So it's not actually very helpful for you to be able to use the equations to come up with coordinates in a table and then plot those coordinates. Computers are better suited for doing that kind of mechanical exercise. But you maybe need to do this a couple of times yourself to just get the experience of the process and use that as a stepping stone before you can jump to understanding or predicting why should equations like this end up looking like that. And the key to doing this is to actually try and visualize the motion of x and y separately. So let's start with the table. Like the table here can help us start to visualize the motion. We see that as time starts at 0 and goes up, the y-coordinates start at 10 and go down. So if you imagine that as a motion, we don't know what's happening with the path going left and right, but we know that from time equals 0, we're going to start at 10 and be continually moving down. All right, so as we're continually moving down, what else is happening? The x-coordinates are starting at 4 tenths, going to 0, and then going back up. So very roughly, we have the idea that you've got a continuous downward motion, and at the same time, you've got an x position that is moving left a little bit and then right a little bit. So that's enough to get this kind of overall shape. As I move down, my coordinates are going left and then right. So how would you have gotten that same intuition without plotting all those coordinates. Instead of making a table of values, which takes a really long time, it's better if you can use your understanding of the shapes of the basic families of functions and transformations of them to plot the x of t and the y of t functions separately, and then use those graphs to help visualize the motion of the x coordinate and the y coordinate. So let's start with the y of t function here. So I know that this is a line with a slope of -1 and a y-intercept of 10. So if I'm going to plot it, that's very fast. Looks like this, goes that way. Whoa. Sorry, my tabletop is, it's a little bumpy. And that helps me imagine that as time is going up, the y-coordinate is just decreasing. All right, so what about this one? I'm recognizing that this is a parabola. I know because of my transformations that this is a right-shifted parabola by 2. So let's make the vertex over by 2. So then I know that if I move 2 away from the vertex, in the numerator here, I will have a value of 4, because that's what 2 squared is. But then I'm dividing everything by 10, which has the effect of kind of squishing the whole graph vertically by a factor of 10. So I know it's going to be something like this. So let's call that 4. So parabola, and then it's symmetric, and then it just keeps going up out that way. All right, so how do these two graphs help us? We can use those two graphs to try and guide our pen and our thinking about what happens when you combine those two directions of motion together. So here, this x-axis is now actually the x position, not time. That's actually the y position. So I know that, again, from this graph, my y position should start at 10 and be moving slowly downwards. Meanwhile, I know that my x position should start at, that's 0.4, should start at 0.4, go to 0, go back up to 0.4 and out. So if I was going to graph only my x positions, I know I'm here, going that way, and then back out that way. So if I put those roughly together, I've got something like this, and I'm just going to move my pen continuously downward at a constant rate because I see that that's what the graph is telling me to do. And I can just move like that. And I don't know exactly where the x-intercept is, but I do know it's in the shape of a parabola that kind of goes out in this direction. So this takes imagination. Like, you have to build your ability to imagine combining these separate motions, and that's hard. It doesn't happen right away. However, it's a heck of a lot easier over time, and it's going to be a more powerful mental tool for you to be able to do this than plotting a bunch of points in a table. So if you have to make a table of values, that's okay for the moment, but I'd like you to really try and wean yourself from that and practice this idea of visualizing motions of x and y separately. Now you try it. Go ahead, you can either use a table or two graphs, but I want you to tell me what is the rough shape of the path defined by this parametric set of equations, and what's the direction of travel. So I've graphed x of t and y of t separately. I can see that my x-coordinate starts at 10 and decreases. So my pen is going to start at an x-coordinate of 10 and move continually that way. Meanwhile, the y-coordinate starts at 0 and goes up like a quadratic. So my y-coordinate will start here and go up at an increasing rate. So what that should end up looking like is something like this. It's a half of a quadratic function. We didn't plot that part of it. And the direction of motion is from right to left and from down to up.